Good morning, student. Today I'm going to discuss with you the adherent points and closure of our set. So first of all, let me define what is an adherent point. So far we have defined what is an accumulation point in the class. Now let us discuss what is an adherent point. You have S to be a subset of Rn and alpha bar belong to Rn. Then alpha bar, this point alpha bar belong to Rn will be called an adherent point of S if for each R greater than 0, mean for each positive real number, the intersection of every open ball having centered at alpha bar and radius r with S is non-empty. So alpha bar belong to Rn will be called an adherent point if the intersection of every open ball having centered at x alpha bar and radius r with S is non-empty, means there exists at least some point which is common to this set. And note that adherent point alpha bar will be an adherent point if and if every open ball having centered at alpha bar and radius r contains at least one point of S, means their intersection will be non-empty. For example, every finite set only the member of this finite set will be an adherent point. Why? Because if you have 1, 2 and x1, x2, x3 are three elements of this set S, then you take an open ball around each of this. So any open ball which is around this point x1 will always contain a point of this set. In particular, it contains x1. So therefore, x1 is an adherent point of this set S. Similarly, x2. But if you take any point outside this, for example, if you take outside 3, then no member outside this x3 will be no member of outside this x1, x2 or 3 will be an adherent point, because there exists at least one open ball which contains whose intersection with this set S is an empty set. So by adherent point mean each and every open ball, if and only if every open ball having centered at that point, if you take alpha bar to be x1 or x2 or x3, then every open ball having centered at each of this point and any radius r, their intersection with S will be a non-empty set. For example, this is x1 you have here. If you take a ball here, then no members outside this set S, okay, will be an adherent point of S. Why? Because there exists an open ball having centered at that point, say xi prime, which contains no point of this set. But each and every member of this set will be an adherent point, because as you can see that every open ball having centered at x1, for whatever r you take, it will always contain a point of S. Their intersection with S will be non-empty. Similarly with x2 and x3. But if you take any S subset S here, an open interval 0, 1, then you can say that a point outside the member of open interval 0, 1 will also contain will be a limit point, will be an adherent point, because for example, if you take this point 1 here, this is open interval 0, 1. So you take here this open ball 0, 1 having centered at 1 and radius any r, you can see that every ball having centered, every open ball having neighborhood at this one will be an adherent point. Why? Because it will always contain a point of S, means the open ball having centered at any point inside this. But if you take this one outside it will not contain. So every point which lies, including 0 and 1, they are all adherent points of S, because every open ball having centered at 0 and 1 or any point you take inside here will always be an adherent point, because the intersection of those open ball having centered at, say, any x bar you take here, or any x bar in particular equals 0, will always contain a point of S, that is B x bar r intersection S will always be non-empty. So by adherent point means if every open ball having centered at that point, their intersection with S is non-empty, then such a point is called an adherent point. By closure of a set, let S be a subset of Rn, then the closure of S denoted by S bar, that is the collection of all adherent points of S, collection of all point x bar belong to Rn such that their intersection with S is non-empty, then S is said to be the closure of S, and it is denoted by S closure. So in this case, in case of this 1.01, okay, so members outside this set S also can be an adherent point, because if you take those numbers which are very close to 0, then or a very large zero having centered at 0, therefore they are all adherent point because it can contain at least some point of S. So therefore this is an example of an adherent points where members outside the set 0, 1 also can be an adherent point of S. Whereas in case of a finite set, only members of a finite set can be an adherent point. No members outside the set S can be an adherent point. Now let us see some important result on closure. S here is a subset of Rn. Then prove that S closure, which is equal to, in some definition they use S union D of S, is defined as closure or the collection of odd points x bar belong to Rn such that B x bar R intersection S is non-empty. This is a definition of closure, either this or this for any R greater than 0. So let me prove this first result. S closure is, so to prove S closure is closed, I need to show that Rn, the complement of this Rn minus S closure is open. Okay. So for if this is equal to 5, then there is nothing to prove. But suppose this is non-empty. Rn minus S closure is non-empty. So you take x bar belong to Rn minus S closure. So if x bar belong to Rn minus S closure, it implies that x bar does not belong to S closure because it belongs to the complement of S closure. So this implies that there exists an open ball having centered at x bar and radius r such that the intersection of this with S is equal to 5, because if it is S closure means the intersection of every open ball having centered at x bar and radius r with S will be non-empty. But since x bar is not an element of S closure, it means that there exists an open ball having centered at x bar and radius r whose intersection with S will be an empty set. Now we have to show that so we take and how to prove this, that is there exists an open ball having centered at this whose intersection is non-empty. So you take any y bar belong to B x bar R, then the distance of y bar by definition of open ball from x bar is strictly less than R. So you take R1 to be the distance R minus the distance of y bar minus x bar. Because this is less than R, so R minus this is still greater than 0. So you draw here a ball, this is x bar and radius R, and take y bar to be a point here of radius R. So clearly this open ball having centered radius R1, clearly this open ball having centered at y bar and radius R1, okay, and radius R1 is a subset of the open ball. This is an open ball having centered at x bar and radius R, subset of open ball having centered at x bar and radius R. So, and since the intersection of this with S is non-empty, so it implies that by bar R1 intersection S also will be an empty set, because this is a subset of this and intersection of this with S is non-empty. So this implies that y bar does not belong to S. But y bar is an arbitrary element. It implies that every open ball having centered at y bar, and since y bar is an arbitrary element of this set B x bar R, it implies that B x bar R is not a subset of S. So if it is not a subset of S, it implies that B x bar R is not a subset of the derived set of S, or sorry, it is not a subset of S closure, because S closure means the collection, because the intersection of this with S is non-empty. So therefore it cannot be as if it is a subset of S closure, it means the intersection of this with S will be a non-empty. But since the intersection of this is an empty set, it shows that the open ball having centered at x bar and radius R cannot be a subset of S closure. So if it is not a subset of S closure, it implies that Bx bar so this implies that Bx bar are intersection subset of Rn minus S closure. If it is not a subset of S closure, it means that this open ball belongs to the complement of S closure. So this implies that X bar is an interior point of this Rn minus S closure, because what is X bar? X bar, we have taken X bar is an element belong to Rn minus S closure, and what we have shown is that there exists an open ball having centered at X bar and radius R such that that open ball is a subset of Rn minus S closure. So but again, X bar is an arbitrary point of this complement of S closure. It shows that each and every point of Rn minus S closure is an interior point. So this implies that Rn minus S closure is open. So if the complement is open, it implies that S closure is closed. So this completes the proof.